Hello, Chemistryos. Happy to have you back in the classroom. The virtual classroom, learning some chemistry with me. It's too bad that your IB exams have been canceled. I was looking forward to you guys really putting in a strong effort and finishing strong and showing that you could learn a million things in just 2 or 3 months. But we got just a little bit left to go. We're going to do some organic chemistry, and then you guys are going to choose an option to learn, and that's going to be it for our chemistry course. But right now, something that's been popular in the news just to get us going back with organic chemistry is a drug called chloroquine, which is one of the early anti-malarial drugs that was synthesized about in the 1940s, 1950s. And there's a lot of talk about it right now because chloroquine, believe it or not, has some activity against, or supposed activity against the COVID-19 infections happening in the world. I thought we can start here by giving you a bit of the story of chloroquine, looking at the structure. The structure of quinine, the anti-malarial drug, is also a very important part of the development of organic chemistry in general. Elucidating the structure got a Nobel Prize, and one of the best chemists in the world, Robert Woodward, was one that was involved in that. But what I thought you guys can do first is let's just take a look at the structure of chloroquine and see if we can name the functional groups. Okay, so we got one over here. These guys are functional groups. I'm sure you can name those. Here's another functional group. And this one we didn't really talk about, but we'll talk about right now. All right, so this functional group. Oh, what is it? This is called a tertiary amine. It's an amino functional group. It's tertiary because it has 3 carbons attached to it. This is a secondary amine. It has 2 carbons attached to it. These are alkyl groups, okay? And this is a benzene ring. It's a strange structure that has double bonds all attached. And this entire backbone is called an N-heterocycle. It's also an aromatic ring. It's a benzene type of ring. And that's the important part of the structure. Okay? So let's take a look at how we can synthesize this. Now, you're not going to be responsible for this, but here's just an example of a organic chemistry's cookbook. But in all these structures, you can also go through it and see if you can name some of these functional groups that are here. Like this is a carboxylic acid. This is a hydroxyl group. I wonder what that is. I wonder what that is. I wonder what that is. All right, so you guys can go through all that. But essentially, what organic chemists do now, normally chloroquine, you would have got that from or quinine you'd get from a plant extract, plants that grow in Ghana. And then that's expensive to grow plants and extract those chemicals. So we had to find ways to synthesize these from scratch. Okay, so here's a commercially available chemical that you can get. Okay, it's an aniline derivative. 3-chloroaniline is what it's called. Okay, and if you react it with this monster of a molecule, okay, and with a bunch of heat, you'll see that this amino group, which has a lone pair of electrons, tends to find the carbon that has most of its electrons taken away from it. This carbon's attached to an oxygen, which is electronegative. It's also attached to all these carbons with oxygens that are pulling electrons away from it. So if I was to take a look at this setup over here, this is the minus of that molecule, and this is the plus of that molecule, and they're going to come together and attach like Lego, like you can see over here. Now, when you go to university in your first year, or probably beginning of second year organic chemistry class, you'd have to memorize this stuff. You'd have to be able to take a look at that structure and see how you can build it from your knowledge of chemicals. It's kind of like the Lego of chemistry that I was talking about. Okay, and now from here, once you've developed that, isolated it, and purified it, you can then react it further, probably with just a little bit of heat and acid, and it's going to close up, and it's going to make that backbone that we were talking about up here. Okay, and then if I treat this with sodium hydroxide loves to break up esters. That's that functional group over there. So it'll turn an ester into a carboxylic acid, which is what you can see over here. And then if I treat that with heat, okay, I'm going to remove the carboxylic acid, blow off carbon dioxide, and then you get that structure. And then when I treat that with POCl3 likes to react with hydroxyls and turn them into chloro groups. That's how we get that backbone molecule. But we're not done yet. After that, you got to do a bunch of other steps to then attach this side group on here, which is important. So what's the importance of this structure? How does chloroquine work when it's treating malaria? Well, this part of the molecule is important for binding to a molecule called heme, like hemoglobin or heme. So it binds to those molecules. And then this part over here obviously has some important roles in the toxicity and how it kills the malaria parasites. Now, this chemical, eventually malaria became resistant to it, so they had to try to find other ways to find new drugs. And often what they do is they take the parent drug and they start to play around with the side chains. You can see here, this is chloroquine, which is really toxic to humans. And then they started playing around with changing these side chains. And all of these are potential drugs called analogs or derivatives that all have different activities. So what chemists would do in the lab is they would just throw 100 different side chains on there and hope that one is going to be more effective. And I'm sure that's what's happening right now to develop drugs for the COVID-19. They're taking this structure and finding any drugs that they've developed over 100 years and just playing around with the side chains and seeing if it'll improve the toxicity and also prevent people from having the horrible side reactions that they get from chloroquine. You heard in the news probably that people are starting to buy it and drink it and they're dying. Well, chloroquine's not the safest thing to be taken. You need to only take it if you're sick. All right, so that's enough for that. Let's get back to what we really are after. And what we're really after is learning about the chemistry of alkenes. Now, we did this right before the break, but looking in your eyes, you guys are pretty tired but when we were doing this. So I just wanted to spend a couple lessons on just reviewing what are alkene functional groups, okay? So in this lesson, we're going to name alkenes, we're going to look at their isomers, and in the next lesson, we're going to talk about general reactions of alkenes and making alkenes. If you take a look at this little video on the side, here's just an example of how an alkene, such as ethene, if you heat it up together, they polymerize. So most of the plastics that we have in Ghana are polyethylene made from an alkene. When you heat it up, it reacts with other ethene molecules to make a polymer, a plastic. So it's a very important industrial chemical. Alkenes are really important for the rubber industry or the plastic industry. And so anyone who's working in that arena is always playing with alkenes. All right, so the general formula of an alkene is CnH2n. Now that's different than an alkane, which was CnH2n plus 2. All right, so we're missing that plus 2. That's gone. All right, so that's the difference. So it's CnH2n is the general formula of it. And if you take a look at the structure over here, you'll see that the alkenes are notified by having a carbon-carbon double bond. Okay, so that carbon-carbon double bond is termed an unsaturated hydrocarbon. Whenever a hydrocarbon, that's any molecule that has carbon and hydrogen in it, has double bonds in it, we call them unsaturated. And you would have heard that term when we talk about unsaturated fatty acids or saturated fatty acids in biology. Unsaturated means that the molecule has a double bond in it. Okay, now for the higher level students, I just wanted to point out this and this. Okay, one of the bonds in a double bond is a sigma bond. That's from the overlap of orbitals head to head. And a pi bond is made from the overlap of p orbitals. So the hybridization of these two carbons would be sp2 and sp2. Okay, for everybody in our class, we also need to understand what the bond angles would be from our bonding unit. So what do you think the bond angles between all of those carbons would be? That geometry would be trigonal planar. Okay, and then in a trigonal planar geometry, the bond angles are 120 degrees. Okay, so that's something that you have to remember from the bonding unit. Okay, and you would have had to been able to do that on the IB exam. Okay, this molecule in front of us is called ethene, as you guys can predict, because eth means two carbons. So how do we go about naming alkenes? Well, we did this right before we left, and you guys did a worksheet on it. The first thing you got to do is you got to identify the longest chain of carbon atoms, which we call the parent chain. In both these molecules, there is 1, 2, 3, 4 carbons in that longest chain. This one is 1, 2, 3, 4, 5. Sorry, that's 5 carbons. Okay, so this molecule is butene. And because the carbon double bond is on that first carbon, we don't have to put a number there. It's just butene, not 1-butene. And then in this molecule is called pentene. Now it's 2-pentene because we have to start counting to lower where that functional group is going to be. So this is carbon number 1, number 2, number 3, number 4, number 5, which makes this 2-pentene. Okay. Like other molecules, there are structural isomers. An isomer is a molecule that has the same molecular formula but a different structure. Okay, the bonds are formed differently. So the structural isomers of alkenes are determined by the position of the alkene within the structure, and they're also determined by the arrangement of the carbon atoms around the alkene. So simple to begin with the structural isomers, if I just change where I put that carbon double bond, so instead of being in the middle, I put it over here, those are two different molecules. They smell different and they behave different, okay, even though they have the same molecular formula. Okay, this molecule here is 2-butene because the double bond is in the middle, and this molecule is 1-butene or just butene. Okay, but they behave different. They have different properties. Okay, now a geometrical isomer also has the same molecular formula. And this molecule here, 2-butene, can have two different versions of it, and it's all based on the arrangement of the carbon atoms around that central double bond. Okay, see the arrangement here looks like a zigzag, and the arrangement here looks like that. They're on the same side. Okay, those are very different molecules. The structure, how they would fit into a receptor in your nose, or how they would fit when they pack against each other to form intermolecular interactions, is going to be very different. So these two molecules, even though they have the exact same bonding structure and the exact same molecular formula, they would even have maybe slightly different boiling points and physical properties. Okay, so the name of this molecule is called trans-2-butene. That's because this substituent, carbon substituent, is on the opposite side. When they're on the opposite side of the double bond, it's called trans. Okay, this carbon and that carbon that are attached to the double bond are on the same side, so that they're called cis-2-butene. Now, I don't think the IB really makes you try to understand that. I just threw that in there to make sure that you guys can see that there's different ways that the structures of double bonds can form, and they all have different properties. Okay, so for organic molecules, the structure determines the physical properties, which is important when we're trying to design drugs and do other things for them. Okay, so let's work on practicing naming some alkenes that I have drawn here below. Okay, so for the first one that we're going to look at right here, how would we name that structure? Okay, you can pause it, but I'll go through it right now. Okay, so first I'm going to count the number of carbons in the parent chain. There's, well, let's change the color here. There's 1, 2, 3, 4. Okay, in that case, this is going to be a butane or a butene. So we've seen this structure already. This is 2-butene. Now, I can't really tell from the way this stick structure is drawn to see whether those CH3s on position 1 and position 4 are on the same side or the opposite side. So I'm not going to put in the cis or the trans. They would have to actually show me that in the way they drew the structure. So that's 2-butene. Now the next structure on the right over here, let's see how we can name that. Well, we've already done this, okay? This is 1-butene, okay? It was just above. Okay, well, that's kind of lame. All right, but doesn't matter. It's good practice for us. And then if I take a look over here, I got the same. I got another 4 carbon atoms, but they're arranged differently. So this one will require some of your memory on how to name alkyl groups. Okay, so it's still going to be, now let's see, I have to count the longest chain. Even though there's 4 carbons, it's not a but anymore because the longest chain is only going to be 1, 2, or 3, or 1, 2, 3. So that's the longest chain, so it's a prop type of molecule. And in this case, I'm going to name it, it's a propene, that's for sure. So 1-propene, okay? But then if I've decided that this is my parent chain, how do I go about naming that attachment? Well, that attachment is going to be a 2-methyl-1-propene, okay? So that's the name of that molecule. That this is a methyl group, 2-methyl-1-propene, okay? I'm going to give you guys another worksheet to practice naming alkene molecules and naming the substituents, but it's pretty easy. All right, thanks a lot.